Good afternoon, everyone. Today we have a session about Silvaco TCAD, and we want to introduce the Atlas environment. First of all, I want to thank the holder of this event, KL University, and also the nanotechnology electron device branch of the KL University. The topics we are going to talk are about the Silvaco company, and after that we go through the Atlas environment, and finally we show a code. First of all, we want to know what is the Silvaco and where it has been originated. Silvaco Group Incorporation develops and markets electronic design automation and technology CAD software and semiconductor design SIP. The company is headquartered in Santa Clara, California, and has a global presence with offices located in North America, Europe, and throughout Asia. Since its founding in 1984, Silvaco has grown to become a large, privately held EDA company. The company has been known by at least two other names, Silvaco International and Silvaco Data Company. TCAD device simulation is a key to develop next-generation semiconductor devices, giving insights into complex physical phenomena. Victory device can execute physics-based device simulation to predict and understand device performance. About the benefits, we can say electrical, chemical, thermal, and optical characterization of advanced semiconductor devices allows for device performance optimization. Understanding the challenges of the current technologies lead to reduced product development time and the exploration of novel device technology for next generation devices. About the applications, we can simulate advanced CMOS, box CMOS, PDSOI, FDSOI, and FinFET. And the power and RF, BCD, power diode, IGBT, three-star gallium nitride HEMT, silicon carbide DMOS, silicon carbide LMOS, and about optoelectronic, we can simulate amorphous silicon, polysilicon, and OLED and micro-LED devices. Let's talk about the Atlas environment. Atlas provides general capabilities for physically based 2D and 3-dimensional simulation of semiconductor devices. Atlas is designed to be used with VWF interactive tools. The VWF interactive tools are DXbuild, Tunipula, DevEdit, Mask Views, and the Optimizer. Atlas is supplied with numerous examples that can be accessed through DXbuild. These examples demonstrate most of Atlas capabilities. The input files that provided with examples are an excellent starting point for developing your own input file. DXbuild provides an interactive runtime environment, 20-plot supply scientific visualization capabilities. DevEdit is an interactive tool for structure and method specification and refinement. Mask Views is an IC layout editor. The optimizer supports black box optimization acts across multiple simulators. Atlas, however, is often used with Atana process simulator. Atana predicts the physical structures that result from processing steps. The resulting physical structures are used as input by Atlas, which then predicts the electrical characteristics associated with the specified bias conditions. The combination of Atana and Atlas makes it possible to determine the impact of process parameters on device characteristics. The electrical characteristics predicted by Atlas can be used as input by the Atmos device characterization and SPICE modeling software. Compact models based on simulated device characteristics can be then supplied to circuit designers for preliminary circuit design. Combining Atana, Atlas, Atmos, and Smart Spice makes it possible to predict the impact of process parameters on circuit characteristics. It therefore links simulation very closely to technology development, resulting in significantly increased benefits from simulation use. Atlas is a physically based device simulator. Physically based device simulation is not a familiar concept for all engineers. Physically based device simulators predict the electrical characteristics that are associated with specified physical structures and bias conditions. This is achieved by approximating the operation of a device onto a 2 or 3-dimensional grid, consisting of a number of grid points called nodes. By applying a set of differential equations derived from Maxwell's law onto this grid, you can simulate the transport of carriers through a structure. This means that the electrical performance of a device can now be modeled in AC, DC, or transient modes of operation. There are three physically based simulations. These are predictive and providing insight, conveniently captures and visualizes theoretical knowledge. Physically based simulation is different from empirical modeling. The goal of empirical modeling is to obtain analytic formula that approximate existing data with good accuracy and minimum complexity. Empirical models provide efficient approximation and interpolation. They don't provide insight or predictive capabilities or encapsulation for theoretical knowledge. Physically based simulation has become very important for two reasons. One, it is almost always much quicker and cheaper than performing experiments. Two, it provides information that is difficult or impossible to measure. The drawbacks of physically based simulation are that all the relevant physics must be incorporated into a simulator. Also, numerical procedures must be implemented to solve the associated equations. These tasks have been taken care of for Atlas users. Those who use physically based device simulation tools must specify the problem to be simulated. In Atlas, specify device simulation problems by defining the physical structure to be simulated, the physical models, bias condition for which electrical characteristics are to be simulated. This figure shows the types of information that flow in and out of Atlas. Most Atlas simulations use two input files. The first input is a text file that contains commands for Atlas to execute. The second input file is a structure file that defines the structure that will be simulated. Atlas produces three types of output files. The first type of output file is the runtime output, which gives you the progress and the error and warning messages as the simulation proceeds. The second type of output file is the log file, which stores our terminal voltages and currents from device analysis. The third type of output file is the solution file, which stores 2D and 3D data relating to the values of solution variables within the device at a given bias point. Atlas has a library of standard examples that demonstrate how the program is used to simulate different technologies. These examples are a good starting point for creating your own simulation. The examples are accessed from the menu system in DeckBuild as shown here in the figure, and also you can refer to the website of the Silvaco and in example part. The input file contains a sequence of statements. Each statement consists a keyword that identifies the statement and a set of parameters. The general format is the statement and parameter value. For any statement, Atlas may have 4 different types of value parameter. These are real, integer, character, and logical. The statement here, as an example, is doping. All other items are parameters of the doping statement. Uniform and n.type are logical parameters. Their presence on the line sets their values to true. Otherwise, they take their default values, usually false. Concentration is real parameter and takes floating point numbers as input values. Region is an integer parameter taking all integer numbers as input. You only need to use enough letters for any parameter to distinguish it from any other parameter on the same statement. Thus, concentration can be shortened to cons. You can set logical parameters to false by preceding them with the caret symbol, and a line beginning with a number sign is ignored. These lines are used as comments. Atlas can read up to 256 characters on a one line, but it is better to spread long input statement over several lines to make the input file more readable. The backslash character at the end of a line indicates continuation. The order in which statements occur in an Atlas input file is important. There are 5 groups of statements that must occur in the correct order. Otherwise, an error message will appear which may cause incorrect operation or termination of the program. For example, if the material parameters or models are set in the wrong order, then they may not be used in the calculations. The DeckBuild command menu can help you to create input files. This menu is found under the Commands button on DeckBuild's main screen. The Commands menu is configured for Atlas whenever Atlas is the currently active simulator in DeckBuild. When Atlas is active, which is indicated in the lower bar of DeckBuild window, an Atlas command prompt will appear in DeckBuild output section. The command menu gives you access to pop-up windows where you type information. When you select the right button, syntactically correct statements are written to DeckBuild text edit region. The DeckBuild command menu doesn't support all possible Atlas syntax, but aims to cover the most commonly used commands. There are 3 ways to define a device structure in Atlas. The first way is to read from an existing structure from a file. The structure is created either by an earlier atlas run or another program such as Athena or Devity. A mesh statement loads in mesh geometry, electrode positions, and doping of the structure. For example, mesh in file uh, equal nMOS dot star str. The second way is to use automatic interface features from DeckView to transfer the input structure from Athena or David, as shown here. And the third way is creating a structure by using the Atlas command language. After GoAtlas command, the first statement must be mesh space.mod equal value. This is followed by a series of x.mesh and y.mesh statements. X.mesh location spacing and also y.mesh location and spacing. The space.mode parameter value is used as a scaling factor for the mesh created by x.mesh and y.mesh statements. The default value is 1. Values greater than 1 will create a globally coarser mesh for fast simulation. Values less than 1 will create a globally finer mesh for increased accuracy. The x.mesh and y.mesh statements are used to specify the locations in microns of vertical and horizontal lines respectively, together with the vertical or horizontal spacing associated with that line. You must specify at least 2 mesh lines for each direction. Atlas automatically inserts any new lines required to allow for gradual transition in the spacing values between any adjacent lines. The x.mesh and y.mesh statement must be listed in the order of increasing x and y. Both negative and positive values for x and y are allowed. This figure illustrates how this statement works. On the left-hand plot, note how spacing of the vertical lines varies from 1 micrometer at x equals 0 and x equals 10 to 0.5 micrometer. On the right-hand plot, because space mult is equal to half parameter, the density of the mesh in x and y directions has been doubled. Automatic meshing provides a simpler method for defining device structures and mesh than the standard method described above. Automeshing is particularly suited for epitaxial structures, especially device structures with many layers such as VCSEL device, solar cells, and automation unburdens you from the delicate bookkeeping involved in ensuring that the locations of mesh lines in y direction are consistently aligned with the edges of the region. In the next sessions, we will talk more about automation. Also, you can refer to this address, YouTube address, and see the video. In this video, I have described more about how to determine the points for meshing. Once the mesh is specified, every part of it must be assigned a material type. This is done with region statement. For example, region number, material type, and position parameters. Region numbers must start at 1 and are increased for each subsequent regions statement. You can have up to 15,000 different regions in Atlas. A large number of materials is available. If a composition-dependent material type is defined, the X and Y composition fractions can also be specified in the region statement. The position parameters are specified in microns using x.min, x.max, y.min, and y.max parameters. If the position parameters of a new statement overlap, those of previous region statement, the overlapped area is assigned as the material type of the new region. Make sure that materials are assigned to all mesh points in the structure. If this isn't done, error messages will appear and Atlas won't run successfully. You can use the material statement to specify the material properties of the defined regions, but you must complete the entire mesh and doping definition before any material statement can be used. Once you have specified the regions and materials, define at least one electrode that contacts the semiconductor material. This is done with the electrode statement, for example, electrode name and position parameters. You can specify up to 200 electrodes. The position parameters are specified in microns using the x.min, x.max, y.min, and y.max parameters. Multiple electrode statements may have the same electrode name. Nodes that are associated with the same electrode name are treated as being electrically connected. Some shortcuts can be used when defining the location of an electrode. If no Y coordinates parameter are specified, the electrode is assumed to be located on the top of the structure. You can specify analytical doping distribution. You specify the doping using doping statement. For example, here we have uniform doping as the first statement here. Analytical doping structures profiles can have uniform Gaussian or complementary error function forms. The parameters defining the analytical distribution are specified in doping statement. Two examples are shown below. Doping uniform concentration equal 1 to the power of 16 and that type region equal 1. In this statement, a uniform n-type doping density of 10 to the power of 16 per cubic centimeters in the region that was previously labeled as region number 1 has been specified. The position parameters also can be used instead of a region number. The second doping, as we can see here, it is a Gaussian, specifies a p-type Gaussian profile, which follows this equation, with a peak concentration of 10 to the power of 18 per cubic centimeters. This statement specifies that the peak doping is located along a line from x equals 0 to x equals 1 microns. Perpendicular to the peak line, the doping drops off according to Gaussian distribution with the standard deviation of 0.05. Atlas sets some limits on the maximum number of grid nodes that can be used, but this shouldn't be viewed as a bottleneck to achieving simulation result. In the default version, 2D Atlas simulation have a maximum node limit of 100,000. 3D Atlas simulations have an upper limit of 20 billion nodes, and this limit is high enough that for almost all simulations of conventional device running out of nodes is never an issue. For most 2D simulations, you can obtain accurate results with somewhere between 2,000 and 4,000 node points properly located in the structure. If you exceed the node limits, error message will appear and Atlas will not run successfully. There is an option to deal with this problem. The option is to decrease the mesh density because simulation with the maximum node takes an extremely long time to complete. The maximum number of regions defined in 2D and 3D atlas is 15,000, and the maximum number of definable electrodes is 200. An electrode in contact with semiconductor material is assumed by default to be ohmic. If a work function is defined, the electrode is treated as a shock-clear contact. The contact statement is used to specify the metal work function of one or more electrodes. The name parameter is used to identify which electrode will have its properties modified. The work function parameter sets the work function of the electrode. For example, here we have at the first statement, it sets the work function of electrode named gate to 4.8 electron volt. The work functions of several commonly used contact materials can be specified using the name of the material. You can specify work functions for aluminum, N-dot polysilicon, P-dot polysilicon, and other metals. The following statement sets the work function for an N-type polysilicon gate contact. Note that aluminum contacts on a heavily doped silicon is usually ohmic. For this situation, don't specify a work function. Lumped resistance, capacitance, and inductance connected to an electrode can be specified using the resistance, capacitance, and inductance parameters in the contact statement. For example, at the first statement, we specify a parallel resistor and capacitor of 50 ohms and 20 picofarads respectively in series with a 1 micro Henry inductor. Note that in 2D simulation, these passive elements values are scaled by the width in which is 1 micrometer. So the resistance becomes 50 ohm per micrometer. Distributed contact resistance for an electrode can be specified using the con.resist parameter. For example, the statement here, the second statement, we can see specify that source contact has a distributed resistance of 0.01 ohm as a square centimeter. Simulations with external resistor with external resistors, capacitors, or inductors must be solved using the block or Newton solution method. All materials are split into three classes: semiconductors, insulators, and conductors. Each class requires a different set of parameters to be specified. For semiconductors, these properties include electron affinity, band gap, density of states, and saturation velocities. There are default parameters for material properties used in device simulation for many materials. The material statement allows you to specify your own values for these basic parameters. Your values can apply to a specific material or a specific region. For example, the first statement, number 1, sets the band gap and low field electron mobility in all silicon regions in device. If the material properties are defined by a region, the region is specified using the region or name parameters. In the material sense, for example, in the second statement, it sets the electron and hole shock-clear Hall recombination lifetimes for region number 2. If the name, for example, base, has been defined using the name parameter in the region statement. Then the statement number 3 sets the conduction band density of states at 300 Kelvin for the region name base. The descriptions of materials then provides a complete list of all the material parameters that are available. As mentioned previously, all materials in Atlas are classified as semiconductor, an insulator, or a conductor. In order to correctly define the new material in Atlas, you must specify the name of the material, the user group it belongs to, and the known Atlas material it is to take as a default material. Once you set these 3 elements up in their appropriate places in the input deck, you can change the specific properties of them using material statement as you would normally do. Physical models are specified using the models and impact statements. Parameters for these models appear on many statements, including models, impact, mobility, and material. And also carrier statistics, impact ionization, and tunneling. All models, with the exception of impact ionization, are specified on the model statement. Impact ionization is specified on the impact statement. For example, in the first statement and also second, we specify that the standard concentration dependent mobility parallel field mobility Shockley-Reed Hall recombination with fixed carrier lifetimes, Fermi-Dirac statistics, and Silverheim impact ionization model should be used. Atlas provides an easy method for selecting the correct models for various technology. The MOS, BIP, program, and arrays parameters for the models, a statement configure a basic set of mobility recombination, carrier statistics, and tunneling models. The MOS and BIP parameters enable the models for MOSFET and bipolar devices, while program and arrays enable the models for programming and raising programmable devices. For example, here in the second rectangle, models MOS print enables the CVT, SRH, and Fermi-Dirac models, while the statement models bipolar print enables the ConMOP, FLDMOP, ConSRH, Auger, and BGN models. If lat.temp is also specified on the model statement, or the temperature parameter differs from 300 Kelvin by more than 10 Kelvin, then analytic model is used instead of ConMOP. The print parameter lists the runtime output, the models, and parameters which will be used during the simulation. This allows you to verify models and material parameters. We highly recommend that you include the print parameter in the model's statement. Several different numerical methods can be used for calculating the solutions to semiconductor device problems. Numerical methods are given in the method statements of the input file. Different combinations of models will require Atlas to solve up to 6 equations. For each of the model types, there are basically 3 types of solution techniques: Gaumel, Newton, and Bloch. The Gaumel method will solve for each unknown in turn, keeping the other variables constant, repeating the process until a stable solution is achieved. The Newton method solves the total system of unknowns together. The Bloch method will solve some equations fully coupled with while others are decoupled. Generally, the Gamal method is useful where the system of equations is weakly coupled but has only linear convergence. The Newton method is useful when the system of equations is strongly coupled and has quadratic convergence. The Newton method may, however, spend extra time solving for quantities which are essentially constant or weakly coupled. Newton also requires a more accurate initial guess to the problem to obtain a convergence. Thus, a block method can provide for faster simulation times in these cases over Newton. And also, finally, Gomel can often provide better initial guess to problems. It can be used for to start a solution with a few Gomel iterations to generate a better guess. Then switch to Newton to complete the solution. Specification of the solution method is carried out as follows. Method, Gomel, block, and Newton. To extract the exact meaning of the statement depends on particular models it applied to. This will be discussed in the following sessions. Solutions are obtained by stepping the biases on the electrodes from the initial equilibrium condition. When the voltage on a particular electrode is never defined under any solved statement and voltage is zero, you don't need to explicitly state the voltage on all electrodes on all solved statements. The name parameter is required and the electrode name is case sensitive. Make sure the initial voltage V step and V final are consistent. As will be discussed due to the initial guess strategy, voltage step sizes are limited. This session concentrates on defining a solution procedure. To save result, use log or save statements. Now we are going to show you a code and generated output files. First of all, we should recall the DeckBuild software. And we open the DeckBuild and we see this environment. We have variables window, output window, and runtime progress window, and also DeckBuild edit environment. We'll start with GoAtlas to recall the Atlas module, and then define the mesh in X direction. The next step, we define the mesh in Y direction with specified spacing. After defining the mesh in both directions, we define the regions. Regions should be start from 1 to every number of regions that we need. The next step would be defining the electrodes. And the electrodes could be defined like this, or if you have know the regions, you can easily write the region here. For example, electrode name drain, region 1 or 2. Or like this, you can define by the X and Y parameters. You should notice that the order of the codes should be followed. I mean, we couldn't change the electrode order with the, for example, materials, because the software will give you an error message. The next step is defining the models, as you can see here, and we have some other models that different than I defined previously. Actually, there are many models in the Silvaco, but because this is a general session and such an introductory, I just define some simple models for CMOS and BJT transistors. But we have other models too. Then in the next step, we define contents here, the work function, and the output that we need to display, the structure, and finally the method, which is Newton here, and we go forward for solve the bias of the contact. Here our contacts are drain and gate. We apply the voltage to the drain and gate. As we can see, the voltage to the drain is started from 0 to 0.5 with a step of 0.1. And all the data would be collected in the log files. Here you can see log output file. And finally, to visualize the structure and the log file, we use Tuniplot module here, and the results are here on the right hand. This is the structure and the output log file. Thanks for your attention, and if there is any question, I will be here to answer.